A split-second delay in an autonomous vehicle's decision could lead to an accident. A missed anomaly in a power grid could cause widespread blackouts. A single undetected intrusion in a defense network could compromise national security. We face unprecedented challenges in managing complex systems. Massive data centers, armies of IT professionals, and so-called intelligent systems that are anything but. For decades, we've approached problem solving by collecting vast amounts of data, processing it to identify patterns, and generating outputs based on algorithms and statistical models. But in an age of increasing complexity and rapid change, this approach is reaching its limits. Today's operations lack causal understanding, and prevailing methods give us only the illusion of understanding, always a step behind, reactive rather than proactive, and struggling to adapt to novel situations and edge cases. With current approaches, we have systems and applications that are too slow, unable to scale, and overwhelmed by complexity. They can't adapt on the fly or handle true concurrency. Their rigid processes, reactive monitoring, and bolt-on security measures have proven inadequate, and the need for constant human oversight, it's becoming unsustainable. At the root of these challenges lies a fundamental limitation: our reliance on a data-centric computing methodology. In the current way of doing things, the expert's gone and the data scientists take over. With DADA X, the decentralized autonomous decisioning agent, we've transcended this paradigm. DADA X isn't just another tool in the tech stack. It's a revolution in computing that's about to make a lot of people very uncomfortable. DADA X is based on a powerful new methodology of causal computation, which bridges the gap between system design and operation, and meets the challenges faced by current data-driven software approaches. In building the DADA X platform, we set out to enable a new paradigm in autonomous agent technology, an intelligent platform that understands. Causal AI, the key to autonomy. Our goal was to build a platform that would push the boundaries of what's possible in autonomous decision-making and control. Here's what we aimed to accomplish. We wanted DADA X agents to achieve decision-making speeds that were previously only possible with hardware solutions, while maintaining the flexibility and complexity handling capabilities of software, making decisions and responding to events faster than any existing system. Our vision was a platform that could seamlessly scale to handle systems of any size or complexity. We aimed to create agents capable of handling very complex, nonlinear models, managing the most intricate multifaceted systems without simplification or compromise. We envisioned agents that could autonomously integrate processes and make that integration operationally transparent in the generation of event patterns which could dynamically manage systems. Our goal was to allow for rapid, even real-time changes to operational processes, enabling unprecedented flexibility and adaptability. We wanted an agent that could not just monitor, but instantly pinpoint and respond to anomalies across the entire operational landscape. Our aim was to handle all operations concurrently, mirroring the parallel nature of real-world complex systems. We were committed to eliminating probabilistic guesswork, ensuring that every decision and action is based on deterministic, verifiable logic. Rather than treating security and safety as add-ons, we aim to make them intrinsic properties of the system itself. Our vision included agents capable of self-regulation, operating within defined parameters without external oversight. DADA X was inspired by original work funded by DARPA at Stanford University. The first key innovation came with the creation of the Rapid Event Pattern Language, which has a semantics based on causally related events. Rapid introduced powerful capabilities. It could describe complex concurrent and dependent activities, it offered sophisticated pattern matching for events, and it provided a way to specify constraints and ensure correct system behavior. But the Rapid project was a research effort, and the focus was on developing the language and its formal foundations, rather than creating a production-grade compiler. DADA X is the only software programmed in Rapide, compiled with Java using our proprietary IDE. The key point, indeed the revolutionary advance, is that the DADA X platform, based on Rapide, can read and manage concurrent state machines, a capability that doesn't exist in any other software today. This capability addresses a serious gap in existing technologies. DADA X uses state machines as the foundation of the causal model, which is the core of each agent. Your model is the X in DADA X. When we talk about models in technology, most people immediately think of data models used in AI and machine learning. But now, with DADA X, there's another type of model that will revolutionize how we build autonomous systems. Causal agent models that are operational models. Let's start with what's familiar, data models. These are heavy models, and they're the workhorses of AI and machine learning. They're created by training on vast amounts of historical data using complex algorithms to detect patterns and make predictions. These models are heavyweight in every sense. They're computationally intensive, consume vast amounts of energy, they need extensive time for training and updating, and they rely on massive data sets. But for concurrent autonomy, you just can't rely on databases. It's too slow. Autonomous applications and systems have to use events. The agent must make decisions using causality based on live events, not based on data. Let's contrast the data-centric methodology with what we do, agent models, which are causal activity models. By comparison, we can consider these light models, computationally efficient and quick to implement. DADA X doesn't train in the traditional sense. There's no need for massive data sets or lengthy learning periods. Instead, it takes human expert-designed UML state machine diagrams and translates them directly into the agent's operational logic. DADA X extends traditional state machines by incorporating causality, which allows for mapping between state machines and real systems and enhancing concurrent analysis capabilities. Our IDE converts UML state machines into patterns using causal operators, which integrates multiple systems and embeds logic. And every event is wired to the logic and state, allowing for concurrent processing. Event patterns in DADA X are about capturing the essence of human expertise, the knowledge of designers and engineers, and baking it directly into the system. Think of these patterns as distilled wisdom. They represent the complex decision-making processes of your most experienced professionals, encoded in a form our agents can understand and act on instantly. DADA X's engineered control, with causality, represents a transformational shift from traditional operator control systems that rely on machine learning. Unlike ML-based systems that provide data-driven insights for human interpretation, DADA X embeds causal logic directly into state machines. This allows for autonomous decision-making and real-time adaptation without human intervention. Where machine learning models react to data patterns, DADA X proactively manages processes based on clear cause and effect relationships. This results in higher precision, consistency, and scalability. While machine learning systems struggle with complexity and variability, DADA X thrives on it, handling intricate concurrent processes with ease. In essence, DADA X doesn't just support decisions, it makes them, bridging the gap between human expertise and machine efficiency in ways that current AI and ML approaches can't match. The DADA X pattern generator captures diverse events on the system message bus, creating a comprehensive map of all event IDs in the environment. With just a few clicks, it automatically generates sophisticated patterns, eliminating the need for laborious hand coding. We've extended Java with an intelligent custom compiler that takes all the activity models from the UML to event patterns. In other words, we're encoding causality into process models. Some AI research teams are working on something called causal inference, the process of discovering causal relationships from data. Causal inference involves complex statistical methods aimed at identifying which factors actually cause changes in outcomes as opposed to merely being associated with them. DAGs attempt to represent causal relationships, but they do so in isolation. They treat causality, time, and state separately. This separation creates a fundamental problem. In the real world, causality, time, and state are intrinsically linked. Instead of treating these elements separately, DADA X integrates causal relations, temporal relations, and state context. It's a holistic approach that captures the complexity of real-world systems. DADA X's unique ability to track causality sets it apart from approaches that infer causality. Rather than discovering causal relationships, causal tracking is about operationalizing them, taking predefined causal relationships as modeled in concurrent state machines and using them to drive real-time decision-making and control. At the end of the day, each of these agent models, causal activity models, is more powerful than a state machine. It's more powerful than a Markov chain, because the agent is truly concurrent. Markov chains are inherently sequential. They represent a system moving from one state to another, one step at a time. But in the real world, especially in distributed systems, multiple events often occur simultaneously. When Markov chains try to model systems with multiple components, they use what's called an interleaving approach. This limitation means Markov chains struggle to represent causal relationships between concurrent events. They can't capture how an event in one part of a system might instantly influence another part. And Markov chains typically lack an explicit representation of time. They model transitions between states, but not the duration of states or precise timing of events, crucial factors in concurrent systems. DADA X causal models, on the other hand, can represent and analyze multiple events happening at the same time, along with their causal relationships. This is vital in distributed systems where many things are happening in parallel. By using causal tracking, we ensure that every decision made by the system is based on an explicit understanding of the causal dynamics at play, as defined by the agent model. This leads to greater precision, reliability, and responsiveness, especially in mission-critical scenarios. With our platform, the journey from concept to operational system is streamlined. Design your model, validate with our built-in simulation tools, and deploy. Your model becomes a runtime autonomous agent, ready to monitor, decide, and act. This change in methodology, moving from traditional coding practices to working directly at the state machine level, represents a significant paradigm shift in software development. Our platform allows developers to go from models directly to implementation with as-is logic, saving time and reducing the risk of human error. And the correctness of the model can be validated using simulated system events. The ability to execute the model in a simulation environment and receive alerts for bad behaviors allows for the validation of the underlying system's correctness. Our platform future-proofs systems for continual evolution because changes can be adopted seamlessly at the model layer. Modify the model and you instantly update the behavior of your system. Changes that would have required extensive recoding can be made by simply adjusting the causal model via the UML diagram. The agility this provides is unprecedented. DADA X provides a scalable and extensible architecture that can accommodate new technologies, platforms, and mission requirements as they emerge. And it enables decentralized contributions. Development can scale across the organization, with domain experts able to continuously refine the agent models to address emerging needs without coding bottlenecks. DADA X agents analyze every event in real time. Today, no software system in the world can do this. In practice, the term real-time is often used loosely. Near real-time analysis introduces latency that can be catastrophic in time-sensitive applications like autonomous vehicles. DADA X agents monitor events faster than an application processes data. Unlike traditional programming environments that struggle with recursive instances, DADA X efficiently monitors and live audits the entire life cycle of each state machine from end to end at the most granular level, which enhances process visibility. Live consolidated audit is as good as it gets. Every event is audited in real time against the causal model. This allows for instant detection of anomalies or deviations from expected behavior. Event patterns are used as triggers and outputs of component state transitions. The system can make autonomous decisions based on its understanding of the causal model and current state. DADA X doesn't use traditional methods for anomaly detection. In our process-centric approach, the system focuses exclusively on monitoring authorized patterns of process events. So any events that deviate from these authorized patterns are identified as violations in the operational process. Using their innate understanding of the modeled activity processes, the DADA X agent can immediately detect deviations, event validation failures, missing events, and timeouts. Currently, no software system in the world, apart from DADA X, can make a decision on a single event as to its correctness. We consider this ability to be a sort of holy grail of information technology. Runtime monitoring for correctness of operation provides security by default. Cybersecurity is not an add-on to our platform. The ability to validate a single event or detect an anomaly autonomously isn't just a technological advancement, it's a game-changing capability. Imagine a network of autonomous drones conducting a reconnaissance mission. Traditional systems might analyze data in batches, looking for patterns over time. But DADA X can validate each event as it happens. If it's an anomaly, countermeasures can be initiated immediately, potentially saving the mission and the drone itself. In cybersecurity, the stakes are equally high. Imagine a military network facing constant probing from adversaries. Traditional systems might only detect an intrusion after it's occurred, by recognizing patterns in log data. But DADA X can validate each network event in real time. A single unusual data packet or access attempt can be instantly flagged and blocked, preventing a breach before it even begins. To really grasp the difference in our approach, let's consider the Next Generation Air Dominance Program, NGAD, a cutting-edge initiative involving a sixth-generation manned fighter coordinating with a team of unmanned drones. This program represents a pinnacle of autonomy and integration challenges in modern warfare. In the traditional programming paradigm, developing the NGAD system is a Herculean task. You'd have teams of aerospace engineers and AI specialists spending years trying to translate complex battle strategies and aircraft behaviors into millions of lines of code. Now imagine tackling the challenge with DADA X. Instead of drowning in code, military strategists and engineers would create UML state machine diagrams that visually represent the operation and behavior of the entire system. These diagrams would capture everything, from how individual drones respond to threats, to how the manned fighter coordinates the swarm, to how the entire formation adapts to evolving battle conditions. Here's the game changer. DADA X takes these diagrams and transforms them directly into functioning autonomous applications. No lengthy coding process, no loss in translation between human strategic intent and machine execution. This isn't just faster and cheaper, it's also better. It's a fundamental shift in how we approach complex systems. We're moving from data aggregation to activity modeling. Instead of trying to infer behavior from masses of data, we're directly encoding the desired behavior of the system. The implications for the NGAD program and all multi-domain operations are profound. Changes in strategy or tactics that would have required months of recoding can now be implemented by simply adjusting the UML diagrams to adjust the causal models. The system becomes inherently more adaptable, able to evolve as rapidly as the threats it faces. DADA X can change how we program the NGAD systems, fundamentally altering how we conceptualize and implement complex, autonomous military systems. And it can bring us closer to achieving next-generation air dominance with unparalleled speed, accuracy, and strategic flexibility. From defense and aerospace to energy grids and autonomous vehicles, DADA X has the potential to revolutionize industries. The challenges we face in the 21st century demand solutions that can match their complexity. By harnessing the power of causal computation and true concurrency, DADA X offers us a path forward, a way to more quickly develop autonomous agents for operational control with decision-making processes that are transparent and auditable.